Sergio from Cambridge, and we're staying on the predictive team. We're not.
Thank you very much. Yeah, thanks for all the organizers for a wonderful conference. So yeah, I promise I won't show any parameters or very few parameters. This is a predictive talk. And as you'll see, it combines ideas from especially yesterday's talk by Susan and also some of the talks we heard yesterday afternoon on pack-based. Okay, so just as a I promise I didn't plan this, but this is a talk about frequential learning. So I'm using this term that is quoted from a landmark work by Phil David in 1984. Sequential learning also goes by the name of online probabilistic forecasting. It's essentially the idea of, predicting a sequence of observations and evaluating the one step ahead predictive distributions. And so just to lay out the set up the problem, we'll consider Zi to be an exchangeable sequence of random variables. And each data point has a sort of regression type structure. So we have an input and an output. And we're going to call a context a history of observations of the following form. So we have the input output pairs for the first k observations, and then the input for the k+1 observation. And the object that we're interested in studying is the conditional distribution of the next response given this context of observations. Okay, so this is what we're calling P0 CK, where CK is a context. And so the object of interest is a mapping from contexts to probability distributions in the output space. And so the goal is to find a predictive model that approximates P0. And our estimator, P hat, will be trained on a data set, which I'm going to take throughout the talk to be a set of IID copies of the sequence Z1 to N. Okay, so this is what I'm calling Z1 to N with a superscript J. Okay, so N is the length of each sequence and M is the number of sequences. Okay, so we start by defining how do we evaluate this prediction model. So we use a frequential loss function. So this is a function that evaluates an object P with a new sample Z1 to H, and it simply scores this predictive probability on each step of the process. Okay, so here S is a proper scoring rule. So for example, you could be using the log score. Okay, so this is the most typical choice. And here, notice that I'm defining a horizon. Okay, so this loss function implicitly says that we want to evaluate these predictives up to some time point H, or some maximum context size H. And so using this loss function, we can define a risk. Okay, so the risk, which I'm writing R P hat for some predictor P hat, is simply the expectation of the loss on a new test point. Okay, so Z1 to H is a new data sequence that comes from the underlying distribution, and so it is a copy of these are IID copies. They're identically distributed as Z1 to H and independent. And notice that because I'm assuming that for convenience, I'm assuming that each sequence is exchangeable, and so I can write the risk also by randomizing the order of the observations, right? So I can introduce here a random permutation of the integers from 1 to n, and here I'm considering, and here I have a sequence of n observations, and I'm just taking the permutation and looking at the first H sequences. So this identity here is just a consequence of exchangeability. So based on this idea of risk, we can also define an empirical version. Okay, so this is what I'm calling the empirical frequential risk. And it's simply an empirical approximation of this of the risk, where we are reusing our data samples. Okay, so the sequences Z1 to N superscript J to approximate the risk. Okay, so just again, notational reminder, so M is the number of sequences in our data set. N is the length of each sequence, and H will be our loss horizon. So the loss horizon can be, in general, shorter than the length of each training sequence. Okay, so why am I interested in this setting? So in recent years, there's been a lot of interest in modeling this type of object, P0, with neural networks. And this is typically done by some form of empirical risk minimization, and many procedures actually minimize the empirical risk that I introduced in the previous lectures, in the previous slides. It's this this kind of average where we're randomizing the order of each sequence. The general idea is that, if S is a proper scoring rule, and the true family of predictives F0 is in this class F over which we're minimizing, then P0 will be a minimizer of at least the expectation of this empirical risk. Okay, and by strong law of large numbers, we expect this to converge, the empirical risk to converge to the risk as M goes to it. Or to converge to this expectation as M goes to it. Okay, so this is, it's a fact that I think Susan mentioned in her talk in the context of the log score, but it holds for more general score. So we could do this with the energy score, any proper scoring rule. So what are some methodologies that have been introduced in recent years? So notable examples are the neural process family of methods and prior fitted networks, which Susan talked about yesterday. And the way that these different methods, there are different kind of axes of variation. So you have methods that use different types of architectures. So some of them will use neural networks to encode each data point in the context, and then these are mapped to some embeddings that are then summed or averaged. But people have started using transformers, convolutional networks. Okay, so there are many different architectures you can use. You can use many different types of outputs. So you can model the predictive distribution as a Gaussian and other parametric families. You can discretize the output space, which is what they do in prior fitted networks. You have latent variable models, and people have even tried using diffusion processes and other generative schemes. Sometimes with the energy score, which can be approximated by Monte Carlo. And then there are also variations in terms of the scoring rule that people use, whether you use the log score, the energy score, how you sample the context sets, how you define the distribution of the size of the context sets in training. So I got very interested in this family of methods when one of my students was applying this in a chemistry problem. Okay, so he was using this to analyze molecular data. And we found that it worked really well in practice. It's a little finicky. So as is usually the case in deep learning, training these things is not very straightforward, but they can work very well. They can be well calibrated. And this made me think a little bit about how we can evaluate these things rigorously. So I should say that there are two different ways of interpreting the application of this type of model. Oh, okay, thank you. I better speed up. So you can think of this in a setting where the data is simulated from a prior, which you know beforehand. Okay, so for example, you have a hierarchical Gaussian process, which you can simulate, but then doing posterior inference is difficult. You don't have the very nice closed form predictive distributions. And so you can just simulate data from your prior, and then learn the predictive distributions using a neural network. So in this case, the goal you can think of as doing amortised inference for the predictive distribution. And in this setting, it makes sense to set N to be the horizon. So the length of each sequence, there's no need to simulate sequences longer than the horizon that you're interested in. Okay, so here's an example that is a bit more complicated than a hierarchical Gaussian process, where, but it's still, this is a paper from Google DeepMind, where they produce a method based on Bayesian neural networks that has state-of-the-art performance in a range of spatiotemporal prediction tasks. And the method is really just defining a prior that you can simulate easily, but for which doing posterior inference is quite difficult. The second interpretation of this type of methods is where the data are not simulations from a prior, but they are real data sets. So in this context, you can think of these observations as coming from m different prediction paths. You assume that there is some kind of underlying hierarchical model. And so your predictor p hat acts as a meta learner. So it's aiming to predict well on a new unseen task. And this is akin to doing empirical base for the marginal data prior. And here you're using whatever inductive bias comes from your neural network architecture, right? So how do you ensure that p hat doesn't overfit? Okay, so it depends very much on the architecture you're using, how you're training the neural network. In this context, we can often have lengths of sequences n, which is much larger than the horizon that you're interested in doing inference for. So you want to do inference for fairly short contexts, but you can train on very large sequences. So this is a setting where the idea of randomizing or permuting the data when we compute the empirical risk comes in very handy. Okay, so very briefly, what I'm going to present are just some bounds for the generalization risk. So this is the gap between the risk and the empirical risk. So we saw several talks about this type of work yesterday. And we would like bounds of the decay not only in m, the number of training sequences, but in n, the length of each training sequence. And the key challenges here is that the data are dependent within each sequence. We're assuming exchangeability. So these are not IAD data. And so to deal with this, we'll assume a form of weak dependent structure, which is known as a de Bruijn condition. And the other complication is that the loss has a frequential structure. So each term of the loss is a score of this form, which depends on a whole range of observations instead of just a single observation pair. So the theorems I'm going to present, they mainly draw on this theory of algorithmic stability. So they're based on assumptions that the algorithm we use is stable, that it is not too sensitive to any particular training observation. And there are some, this is a very incomplete set of references from statistical learning theory. The theory here is really quite vast, and I'm still getting a handle on it. This last paper I think is quite relevant, but I came across it yesterday, so I read it 12 hours ago. But there is a lot of work on doing statistical learning theory for dependent data and also in time series. And I think that the closest type of thing is this pack-based bound for meta learning. There are certain differences with what I'm presenting, but it's very relevant work. So the Lipschitz, so what are the assumptions that we're making? So I'm first going to present a very simple theorem. So if we are willing to assume that the loss function is Lipschitz in the first argument, with respect to some distance in the space of probabilities, and we assume this concept of uniform algorithmic stability. So this is really the important concept in the assumptions. So what I'm assuming is quite strong. It tells me that so here dm is a training data set and dm prime is a training data set where we replace just one of the m sequences. And so this is saying if I replace one of the m sequences, the effect of that on my predictive distribution for any context, okay, and it's I'm taking a supremum over contexts and over data sets, it is bounded by some constant beta. And so under this assumption, you can, using very standard arguments from this paper by Bousquet and Alice, which is a simple application of McDiarmid's inequality, you can obtain a generalization bound of this form. And the takeaway is, for many algorithms, you can show that beta m scales as 1 over m. And so this gives you an excess risk. The right-hand side in this inequality is of order 1 over square root of m. Okay, so you get a generalization bound with the standard kind of behavior. But notice that this is not going through studying the complexity of the class in which we're doing empirical risk minimization, or using a prior as impact base, but it's really using the stability of the algorithm. it's using the ability that the algorithm may be exploring it maybe nominally may nominally have access to a very large space, but it's only exploring a very relatively limited part of the space. So now I'm interested, the problem is this is a bound that only depends on m, the number of sequences. I want a bound that also depends on the length of each sequence. And so in order to obtain that, we need to make more complicated assumptions. So I have this modified in it. Well, I'm now going to assume that the score is bounded by some constant ms, which is you can assume in some cases. And the uniform stability condition is slightly different. So now I'm perturbing the data set by changing just one of the m times n observations. So I'm changing one data point within one of the m sequences. And the effect of that is bounded by beta and m. And now I'm making these weak dependence assumptions, which I won't have time to go into, but it's a notion of correlation decay in the vector of responses. So under these assumptions, we can obtain a bound of this form. The bound is now in terms of the stability constant beta mn, and so depending on the behavior of the algorithm, you'll get different upper bounds. So if we, in a very optimistic regime of stability, you could have beta mn decrease be inversely related to n times m, which is the total number of observations. And in that case, the excess risk, the risk that we obtain is of order 1 over m at plus h over square root of n times m. Okay, so this is a slight improvement of what we had previously if the horizon is significantly smaller than the number of samples in each sequence. Okay, so that's all I wanted to say. Validating, I need to caveat this. So how valid are these diversion conditions? Very difficult to validate in practice. It can be motivated in some spatiotemporal applications, but unfortunately, this is really only useful in the second application scenario where we're using real data, right? It may be easy to verify this type of assumption in some if you're simulating from a prior, but when you have real data, this is just an assumption. And some comments on algorithmic stability. So uniform stability is a very strong condition. You can obtain bounds under weaker notions of stability, usually sacrificing the exponential dependence on a delta. Instead of a log 1 over delta, you would have a polynomial dependence on 1 over delta. And there are many algorithms. There's a lot of work on proving stability for different classes of algorithms, for nearest neighbors methods, for Takeoff regularization, and especially for bagging procedures. And there's a very interesting bit of work recently from Solov, Barber, and Willett, where they show that a different notion of stability is obtained by bagging, in a completely distribution-free setting, making no assumptions on the data distribution or the algorithm. And so I'm interested in seeing how far this can be generalized. Okay, so there are some open questions, but I think in the interest of time, I'll stop. Thank you.
We have time for some questions if there are any.
Thanks, Sergio. That's really interesting. I was wondering, so these stability conditions, since you started with neural networks, I know that there are these like Lipschitz neural networks, and I also know there's some work on, framing them as what their limits anyways as kernel machines. There's obviously some limitations to the asymptotic arguments you make, because you need the ratio of the depth to width to go to constant between 0 and 1 normally for them. So these are not the, the like single layer internet thing where you converge to a GP. These are slightly more difficult. I was wondering if they could be used for that kind of stability argument, or if you're like, or is that not possible? Sorry, so these are two classes. So it's Lipschitz networks and it's the expanding arguments.
I'm not familiar with this type of work. I mean, so you mentioned they're using kernel regularization and of some kind.
No, they essentially derive the limits of neural networks where the ratio of depth to width goes to a constant. So they're considering the limit, but the limit is stable in the sense that the depth does not increase faster than the width. And so as long as that ratio is below 1, you can obtain a recursively defined kernel that characterizes this neural network.
Okay, yeah, so are you talking about like neural tangent kernel?
It's related. I think it's related. It's not exactly the same, but it's related work. I can send you some resources. I was wondering if, I mean, maybe it's also a shot in the dark, but I was wondering because that frames things in terms of a kernel machine. And so you're mentioning kernel machines specifically here.
Yeah.
I was wondering if you could.
So this work, so what, in order to prove that a kernel machine for you, basically you have it in a structure where you have some loss which is additive over the data, plus some RKHS norm squared, penalty. And for that type of, Tikhonov regularization, the argument is based on basically some estimates of the RKHS norm in terms of the sub norm of the predictor. And that the only assumptions that you make about the loss part are, it has to be smooth. You make a Lipschitz assumption again with respect to the sub norm of the prediction, the function, the hypothesis. And you need this kind of additive structure. Does that apply in the neural
I don't know.
network?
I would have to double check. It's not immediately obvious to me that it would apply. So perhaps it's missing the mark. I can send you something later.
Thank you. That sounds interesting.
I'm afraid that's the way